Hello, I am Stephen Shackle, responsible for worldwide industrial marketing in ON Semiconductor's Power Solutions Group. Today I'll be covering ON Semiconductor solutions for EV charging stations. As electric vehicles are becoming more popular, the deployment of EV charging stations need to catch up and even surpass the speed at which EVs are growing. This need for rapid deployment of EV charging stations comes from consumers' anxiety about the range of EVs. The expectations is that a charging station is just as readily available as a gas station. This brings us to the next point of charging time. When EVs first started to get real traction in the marketplace, Level 1 and Level 2 chargers were essentially the only options for consumers. Level 1 chargers, which are usually sold with the EV, can simply be plugged into an outlet at home and will require about 10 hours or overnight to charge the EV. Level 2 chargers require a new power connection to be installed so they can deliver enough power to charge the EV in about 3 to 4 hours. Both the Level 1 and Level 2 chargers provide an AC voltage to the car, and the onboard charger of the electric vehicle actually does the charging of the batteries. These AC chargers are considered slow as people are used to getting their vehicle filled with energy or gas within 5 minutes. This is where Level 3 direct current fast chargers come into play. It is these chargers that will help enable the mass adoption of EVs, as they can get the charge time down to a time very similar to the filling up at the gas station. The majority of these fast chargers are around the 50 to 100 kilowatt range that can charge a vehicle in under 1 hour. This is rapidly changing though, as manufacturers are developing and recently deploying fast chargers capable of delivering 350 kilowatts to charge a vehicle in under 10 minutes. This is where we will focus on for the rest of the presentation. First, we will review a typical block diagram of a DC fast charger. The input into the charger will be 3-phase AC from the grid. It will then pass through a rectifier and power factor correction circuit. A normal topology used here is the Vienna rectifier, which will use 600 or 1200 volt diodes and 650 volt switches, whether FET-based or IGBTs. From there, it will transition into the DC-DC block and secondary rectification blocks. There are many topologies to be used here, but a common one is the full bridge interleaved LLC. On the output of the secondary rectification will be the batteries of the electric vehicle being charged. Switching from the main power blocks, there are many other blocks that actually make the system work. ON Semiconductor has solutions for isolation, including optocouplers and isolated gate drivers. ON's new precision op-amps can be used for voltage and current monitoring throughout the system. Looking at the auxiliary power block, ON Semiconductor has strong portfolios in AC-DC controllers, DC-DC controllers and converters, and LDOs. Now let's take a deeper look into the 3-phase rectifier and PFC. The Vienna rectifier has two different topologies to be considered. The first topology, on the left, looks simpler as it only requires 12 devices, 6 diodes and 6 switches. But these 6 switches require a more complex control as compared to the second topology on the right that only uses 3 switches. Taking a look at the second topology, you will see that diodes are placed in series with the flow of power, which will reduce the overall efficiency, making the first topology more efficient. However, 1200 volt diodes are required for the first topology compared to the second topology, only requiring 600 volt diodes, resulting in a more cost-effective solution for the second topology. So in summary, topology 1 should be used for systems requiring high efficiency, while topology 2 should be used for cost-effective solutions. As mentioned before, the DC-DC and secondary rectification blocks have many different topologies to be used. Most commonly used is a full bridge interleaved LLC requiring 8 switches and 8 diodes. Typically we see 600 volt super junction MOSFETs used here, but for systems that require higher efficiency and power density, 1200 volt or 900 volt SiC MOSFETs can be used. In this case, it is possible to use only a single H-bridge. For cost-competitive solutions, IGBTs will be used. The diodes used in this topology are commonly 1200 volt stealth or hyperfast rectifiers. The trend moving forward, though, is to use 1200 volt silicon carbide diodes. On the right, you see a 3-level LLC that is becoming a trend as it requires less switches and provides a low output ripple as compared to the full bridge interleaved LLC. Turning gears, we will now look at the solutions that ON Semiconductor provides for EV charging stations. First is MOSFETs, where ON is the clear number 2 supplier offering a complete portfolio from low voltage to high voltage superjunction MOSFETs. For medium voltage MOSFETs, ON has the lowest RDS ON specs from 40 to 100 volts as compared to competition's latest devices. The 650 volt SuperFET 3 Easy Drive family expands on this leadership by providing the lowest RSP for an Easy Drive superjunction MOSFET while offering the most robust body diode. Having industry-leading performance in silicon is not the complete story though, as you need a package that can efficiently dissipate the heat generated on the die. ON is leading the way with new efficient packages such as the LF pack, the PQFN 8x8, and the TO leadless packages. The SuperFET 3 family of superjunction MOSFETs is very commonly used in EV charging stations. Within this family are 3 different types. First is the Easy Drive version that has an internal gate resistor and exhibits reduced voltage spikes resulting in lower EMI. Next is the fast version that provides the highest efficiency and has designed for hard switching topology. Lastly is the FR-FET version that is most commonly used in EV charging stations. It was designed to provide best-in-class QRR and TRR characteristics that are needed for soft switching topologies like the LLC. This improves the overall efficiency and reliability of the system. The chart in the upper right demonstrates a 0.2% efficiency improvement of the SuperFET 3 FR-FET device compared to the competition's latest equivalent device. This efficiency improvement comes from the SuperFET 3 FR-FET having the world's best body diode among superjunction MOSFETs. Regarding QRR, it is 33% lower than competition and has peak drain to source voltage of 548 volts at a DIDT greater than 850 amps per microsecond. This is 28 volts less than the best competitor. Solutions requiring a cost-competitive option will look toward IGBTs. ON Semiconductor provides a variety of options here that are tailored toward specific applications and topologies. The Field Stop 4, referred to as FS4 above, is available at 650 and 950 volt nodes, with low, mid, and high-speed versions available for 650 volts and low and high-speed versions for 950 volts. The Ultra Field Stop, or UFS, is the technology used for the 1200 volt node and has low and high-speed versions available. Typically, a Vienna rectifier will use mid-speed FS4 650 volt technology, while a 3-phase half-bridge rectifier will use high-speed UFS 1200 volt technology. In both cases, ON Semiconductor outperforms competition. The 1200 volt UFS has both lower VC SAT and EOF characteristics across the current range compared to competition, as shown in the top right chart. The bottom right chart shows the power loss in a 5 kilowatt Vienna rectifier. The 650 volt FS4 technology is compared to ON's previous generation FS3 and competition's H5 technology. The power loss from the FS4 device is about 1 watt less than competition's, resulting in a more efficient solution. To drive these IGBTs, an isolated IGBT gate driver will be needed. The NCD 57000 device is the preferred gate driver to do this. It provides high current, 4 amps for source and 6 amps for sink at the Miller plateau voltage. This high current drive at the Miller plateau voltage is the main contributor to the 16% energy savings for E-ON compared to competition as depicted on the chart to the right. The galvanic isolation can withstand greater than 5 kV and a 1400 volt working voltage. The NCD 57000 has an array of features that increases the safety and reliability of the system. Some of these features are DSAT, gate clamp, Miller clamp, and a tight undervoltage lockout. In addition to isolated IGBT gate drivers, ON has a family of non-isolated IGBT gate drivers, opto-isolated gate drivers for IGBTs and MOSFETs, and standard MOSFET gate drivers. EV charging stations looking for the highest efficiency and power density will turn to silicon carbide MOSFETs and diodes. On the left side, we have a silicon superjunction MOSFET solution implementing a 3-phase Vienna PFC and series full bridge LLC. On the right side, we have the silicon carbide solution in a 3-phase half-bridge rectifier and full bridge LLC topology. The results are that the silicon solution is only capable of 16 kilowatts with an output current of 20 amps, while the SiC solution is capable of 20 kilowatts with an output current of 35 amps. SiC does this in a solution that is 62% smaller, 22% lighter, and with 20% fewer parts. Today, ON Semiconductor has a full portfolio of 650 volt and 1200 volt silicon carbide diodes, with 1700 volt being released throughout the second half of 2019. In regards to SiC MOSFETs, the 1200 volt 80 milliohm devices released, with 20, 40, and 160 milliohm devices releasing in December 2019. ON Semiconductor is committed to a complete vertical integration of SiC from substrate to final assembly in discrete and module packaging. In addition to SiC devices themselves, ON has developed specialized SiC drivers, and to aid in design, we have physical device models for simulation. Our SiC devices also have a patented termination structure which provides superior robustness for harsh environmental conditions. Up to today, most designs have been using a discrete approach, but as designs are becoming more mature, a move to power integrated modules, or PIMs, will occur. This is driven by how PIMs streamline the assembly process, resulting in shorter production times, simplifies the mechanical design requiring less engineering resources, and eliminates development risk by offering guaranteed performance. In addition, PIMs simplify the manufacturer's supply chain with reduced component count. ON Semiconductor offers a variety of module types as depicted here and owns the complete supply chain including substrate, die, and packaging. Voltage and current monitoring are crucial elements to any power design. For this, op-amps are used but often given very little thought. However, the new current sense amplifiers NCS21XR series and zero drift precision op-amps NCS333 series from ON Semiconductor are providing a significant system improvement. Comparing the NCS213R to the standard LM2904, we see only a 3 millivolt shunt drop is required to achieve a 2% offset error for the NCS213R. A 350 millivolt shunt drop is required for the LM2904. This large reduction in voltage drop across the shunt resistor will decrease the power loss of the shunt, resulting in improved system efficiency. Thank you for your time today. Please take a look at other webcasts in this series on solar inverters, energy storage, and energy infrastructure as a whole. For more information, please visit onsemi.com.